Hello again, everyone. We are now moving into our final presentation session by HP on digital manufacturing, far, future, and near present. I have joining me today Edward Davis, Director of 3D and Digital Manufacturing Strategy. Ed Davis has over 30 years experience in printing technology investigations and product, including over 10 years driving HP strategy in 3D print and digital manufacturing. Current responsibility translating megatrend and competitive analysis into the vision for the digital manufacturing industry and developing the execution strategy for creating this manufacturing ecosystem from design through production and use. Welcome, Ed. Thanks for joining us.
Hey, thanks. Having a little problems with the sharing, just like our friends in the last one.
Oh no, I will wait until you have it.
Let's see. My application doesn't seem to come up.
When you press share screen, there's a section at the top where you can press application. Did you try?
Yeah, no applications show up. Let me see. What if I try the entire screen? I have nothing to hide. Can people see my entire screen?
I can see it.
Okay. All right. Cool. So then let me just go straight to the presentation. Can you see this well?
I believe if you press full screen, it should be great. Awesome.
Okay, we're cool?
Thank you, Ed. I'll hand it over.
Okay, great. We've got a lot of topics to cover today. I've got 45 minutes. I'm going to talk about a lot of things. Going to go way into the future with megatrends, clarify some terms just to make sure that we're all on the same page, and then talk about the changes which are necessary not only in the 3D printers, but also in the design tools for us to fully realize the vision of the future. And then I'm going to talk about how this evolves over time at the end. So starting with the megatrends. Megatrends is not an HP term. It means major social, economic, or technology trends that tend not to change year over year. This is why they're called megatrends. And so HP, we do an analysis of the megatrends for ourselves because, in fact, what we want to make sure is that we're looking far enough into the future, because our full intention is to be in business 10 years from now, 20 years from now. And we have to contemplate what are the sorts of people that we need to hire, what is the sort of talent that we need to develop, what processes we'll be using internally in the future, who are our customers, what products are they interested in, and then we need to keep up to date with business models. So we do this megatrends analysis for ourselves. Having said that, we also have our megatrend analysis free online. I'll give you the link at the end of the conversation. There's others that do megatrend analysis. They do secondary research. You can pay for that megatrend analysis. If you're just interested in getting a good overview, you can go to the HP site. It's free. Okay. So then below these major megatrends, now these four megatrends that we're showing at the top, we, HP, have determined that they're the most relevant for us. And so we break them down into themes. Rapid urbanization is, the tendency of people to go where the money is, the tendency of people to go to major urban centers. I don't mean that means people moving into cities. What I mean to say is, if the jobs are in Los Angeles County, people go to Los Angeles County. The whole world is aging. Again, this doesn't change year over year. What happens is we have, at least in the developed world, fewer than 2 births per couple. So on average, the age of the population is growing. Hyperglobalization, you could say, is hyperconnectivity. So everything connected, digital platforms, the need for security, and then accelerated innovation. Now, what I've highlighted in blue are the topics that I'm going to try to pull together in a story at the end. Okay, so wait for the story, should be interesting. But before getting into that, I need to get into some terms, just because very oftentimes, even within HP, we mix up these terms. First one is Industry 4.0. You'll notice that I spelt it like you spell it in Germany, and I spelt it like you spell it in Germany because the term was coined in Germany in 2010 by a consortium in between the government, industry, and academics. And I've translated it for you into English and simplified it. But if you look up the real term, this is the essence of it. It's using the data across the entire product life cycle, including concept development, product development, manufacture, use, repair, and replacement, to improve the entire ecosystem in that whole product life cycle. So it is beyond manufacturing. Industry 4.0 is not manufacturing 4.0. It's broader than manufacturing 4.0. Manufacturing 4.0 could be considered the smart factory. The smart factory, in fact, is a subset. And what it means is you have things that you're measuring in the factory, and you're using the data in the factory to improve the manufacturing processes themselves. 3D printing can be a part of a smart factory, but it doesn't have to be. It could be a form of digital manufacturing. And then the fourth industrial revolution, we're going to talk about what are those four revolutions, just so that everybody's on the same page. But I'll do that after I go through and deep dive into Industry 4.0. Industry 4.0. So I took the product life cycle and I assigned different phases to that product life cycle. In some cases, I've de-emphasized the importance of something like product development. Of course, there's concept phase, investigation phase, development phase, but I've given it just one bubble to de-emphasize it. And manufacturing, I've given 4 bubbles: part fabrication, sub-assembly, product assembly, and product distribution. This is what you would call the smart factory. And I've given this 4 different bubbles because a lot of times in the 3D industry, we talk about part fabrication as though that's manufacturing. That's not normal manufacturing. For multiple part products, you need to do assembly. Okay, so I'm emphasizing that. My bubbles were too big, so I gave sale and installation only 1 bubble. And then there's use and repair and product replacement. Now, as this is drawn, it looks like there's a perfect digital thread across that whole product life cycle. But the fact of the matter is that real manufacturing happens like this. That product development very often is in a developed country, say Germany, the United States, somewhere. And then manufacturing is generally in less expensive countries. And so what happens is product development has a bunch of data, failure mode, engineering analysis, quality tests, quality results, what they believe makes a product function. And they pass that information to the part fabricators, the sub-assembly houses, the top-level assembly houses, normally through an email. Believe it or not, normally through an email. And then a guy gets on a plane. Those little guys running are normally guys getting on a plane and going to a different country and explaining the email. The whole information flow going from left to right is slow. You could say that the average delay time is around 2 weeks. The situation is worse when you're over on the right-hand side, you're a product repair guy, and you find a new issue in the field, something that you don't understand the root cause analysis of. And so you have to go backwards through that whole value delivery system to try to figure out what the root cause is. It could be that something went wrong in distribution, something broke in the distribution. It could be that it was assembled incorrectly, that the parts were not of the quality that they were supposed to be. It could be that you don't have design margin and they should have caught that in product development, or it could be that the product is being used in a way that you had not anticipated, and you can't control the way people use products. And so the information going from right to left is even worse than the information flow going from left to right. And so the first thing to do, and we've talked about this in many of the talks, is you got to get that data into databases. You've got to get the data from product development into a PLM system. You've got to get the information from all the part manufacturing, sub-assembly tests, product assembly tests into another database, and have that information available, so at least you don't have to wait for a guy to send email or get on a plane to explain something to you. But Industry 4.0 is more than that. Industry 4.0 is in fact taking all of that data from those databases and automatically looking for correlations between bubbles. For example, if a product fails, you look for the correlation to the sub-assembly or the part quality, and you start to automate the alert messages that you send to people. You don't replace people. You just alert them that they need to take action, that something seems to be going wrong. This is industry, what people consider the data analytics of Industry 4.0. And in fact, it's not a straight line. The intention of Industry 4.0 is to close that loop around all of those bubbles and use all of the information from all of those bubbles to make every single phase in that cycle more efficient. And at the heart of that is what they call digital twins. Now, there's more than one digital twin. There's factory supply chain digital twins, which is a simulation of that factory part flow. There's the manufacturing process digital twin, and then there's the product digital twin itself. For example, if you have a 3D printer, the product digital twin is the correlation between the critical parameters of the printer and the part quality. And that's Industry 4.0. Now, the truth is you can gain some efficiencies in manufacturing through Industry 4.0, but the real winners in this are the OEMs. They're the people who make products, because now you can make more competitive, more complex products in less time and with less money. And so the real winners here are OEMs, not necessarily the manufacturers. Okay, so what happens if the part can be digital? Now, for those of you who follow HP, you'll know that when we announced the technology, we talked a lot about voxel control, because we shoot dots on our thermoplastic powder and then fuse. And what we talked about is that because we have dot by dot control, we can eventually develop agents, the stuff coming from the pens we're shooting, that can manipulate properties. Now, the simple thing you could do is mark the part number on the part with color agents. There are, in fact, other agents that are only visible under certain light conditions, so you could, in fact, even hide the marks if you wanted to hide the marks. And then, of course, if you have electronic inks, you can start to embed electronics, and then this is a real smart part. Now, for those of you who do follow our marketing communication, you'll notice in the last year that we don't talk much about voxel control, and we don't talk so much about it, not because it's not our vision of the future, but because all that voxel control is only academically interesting unless you can get into manufacturing. And so we're focusing now on getting into manufacturing. As an example, you would not prototype the embedding of electronics if you could not manufacture the embedding of electronics at the quantities, at the quality that you're interested in. And so voxel control, while it may be long-term and strategy, is in fact later in the game, because the first thing we need to do is be clearly in manufacturing as an accepted manufacturing process, and that's our focus today. There's other challenges of realizing this voxel control. So if you go back to 2014, I think the video is still on YouTube. If you Google something like multi-jet fusion chameleon, you'll see a visionary video come up. And in this video, we explain in the term, not next year, not 2 years from now, but in a couple decades from now, maybe 3 or 4, we should be able to print complicated electromechanical mechanisms like this electromechanical robotic chameleon without having to have further assembly. That's the long-term vision. Now, the challenges are several. First, we need to invent all of this voxel control, and that's going to take us some time. But secondly, if you could print an electromechanical robotic chameleon, how are you going to design it? Would you pretend to say voxel number 1 has this mechanical property, voxel number 2 has this mechanical property and this electrical property and this color voxel? You can't do voxel by voxel design. It's an impossible task. It would take the guy 3 decades to design this. And so what has to happen as we evolve our voxel control technology is we need changes in design tools that facilitate that complex designs can be made. And so there's a term, it's not HP term, called generative design. I'm going to explain what generative design is because this plays into the big story I'm going to tell at the end. The general design process is more complicated than this, but the general design process is the design engineer determines the design intent. I need a mechanism that does this. It needs to fit within this space. It needs to weigh no less than this. It needs to be connected to the rest of the mechanism here and here. Then the designer goes to the CAD tool and generates options. Then the design engineer goes to the simulation tool and simulates how well his options meet his requirements. And then he goes through and optimizes, goes through as many loops as possible. The only difference with generative design, the process is the same, but in this case, the design engineer sets the design intent, and then the CAD tool is integrated with the simulation tool. Now that's the important part, is that the simulation tool needs to be simulating with the knowledge of the process of fabrication. So the CAD tool simulates while generating options and then presents the options to the designer. For example, he said, look, I generated 10 options. None of them are perfect. I calculate that options 3 and option 7 best meet your design requirements, but your restriction number 5 was the tightest. And if you could open that up, I can do another round of optimization. So you see what happens then is that the designer is still in the loop, but his job becomes more engineering and not CAD jockey, right? And so then, how is this going to break up over time? So this is a slide we shared probably around 2014 as well. The slide actually doesn't say much. It just says that we intend to lead the transformation with our ecosystem of partners. It doesn't say anything. But what I want to do is call out those 4 eras of industrial revolution. The first was mechanization and steam. The second was electricity and production lines. The third was computers and robotics. And then the fourth is this Industry 4.0 that we explained earlier in the presentation. So then how does this break up over time? Now here's the story. Here's where the story goes, and you're gonna love this complicated frame. So first, the horizontal axis is time. All right. So every column is a different era of time. Now, everybody knows that eras you don't go to sleep one day, wake up the next day, and you're in a new era. There's overlap, but let's just pretend that they're distinct eras of time. The top column is what needs to change in design and simulation tools. The bottom is what needs to change in manufacturing. Now, to explain the frame, I like to go all the way to the future, all the way to the far right, to the smart products. I hope everybody sees the megatrend of automation. Because it's coming. The automation of cars, the automation of everything is happening. This is the far, far future. So in this smart products phase, this is way out. Don't worry, this is beyond the lifetime of many of us. Smart products talk to each other. They design themselves. They repair themselves. They eventually start to wonder, what are humans doing? And then as everybody has seen in the Terminator movie, they decide to get rid of the humans because we're not doing anything but taking vacation and drinking beer. So that's the final phase, but don't worry, it's a long time from now. I don't know why, but we keep on moving towards that. All right, now to get to that level of automation, I'm gonna focus on the top row. To get to that level of automation, you have to have design and simulation tools that allow non-professional engineers to make something as complicated as the electromechanical robotic chameleon without failure and without safety issues. The level of simulation that's required is decades beyond us. Today, if people understand, if they do mechanical engineering simulation, you know that our simulations are just an approximation of the truth, and they're not as complicated as an electromechanical robotic chameleon. And so this democratization of design of complex things is decades away. To get to that level of automation, you at least need to have generative design tools that allow professional engineers, like most of the people on the call, to do complicated electromechanical designs. To get to that, you at least need the design tools that allow you to get feedback for your additive manufacturing processes, and then the first phase, this short run disruption, is kind of where we are today. So jumping down to the bottom row. So first, when we develop a better, faster, cheaper way of printing, then we can compete for some of the short run manufacturing. We can only change how, because in fact, the design tools don't really enable complex designs, not just yet. And we can only change how, because no supply chain manager in their right mind will have a non-redundant supply chain. What I mean to say is, you normally look to have at least 2 or 3 vendors that can do any given component. And that's because things like hurricanes happen. And if you have a vendor who's in Florida and a hurricane happens, well, you still need parts. Or if you have a vendor in China and COVID happens, well, you still need a vendor that needs parts. And so your redundant supply chain, while there's not a great proliferation of 3D printers in the world, your redundant supply chain are your analog processes. Okay, so now what happens is, when we make the better, faster, cheaper 3D printers, it creates what I say, a creative tension with the design tools. What I mean to say is, just like in the late 1980s, early 1990s, where you would come with a better PC processor, and then the software would improve and eat up all the processing, and 3 months later you have to buy another PC processor. This creative tension between hardware and software starts to happen. So by making these better printers, we're putting pressure on the CAD and simulation manufacturers to make a better design and simulation tools, which then creates more demand for the proliferation of 3D printers around the world, which is this box that I'm showing here that says changing who, where, when, and how production. That's the re-engineered supply chain. Now, both these innovative design tools and this proliferation of manufacturing of 3D printing need to happen for the 4th phase to happen. And what I mean by this change who, where, when, how, what you can imagine is, in the future, you will have 3D factories in every major urban center of the world. Why? Because that's where the people are. That's where the business is. And so you can find, not necessarily in everybody's neighborhood, but maybe in every major urban county of the world, you have this supply chain. Both that and the design tool are necessary for that 4th phase. And notice the 4th phase, I did not call the democratization of design phase that everybody jumps to right away when they talk about 3D printing. What I call it is the hardware innovation phase. And why is this? It's because now the printers are in every county or major county of the world. The design tools are simple. So I have an idea. I call Janet on the phone. I say, yo, Janet, what are you doing? And Janet says, look, I was going to go to lunch with my digital twin. And I said, wait, Janet, take your lunch with your digital twin some other time. Why don't you beam yourself over through your Zoom Halo room? I've got an idea. Let's work on the idea. Janet and I, on a Saturday, we work on the idea. We print one version. We like it. We test it. It works as we anticipated. We upload that file to the internet. If you like it, you download the digital right to print one copy. So now, because of this proliferation of supply chain, Janet and I don't have to have contacts in manufacturing, nor do we have to manufacture. If people buy our design, they get the digital right to one. If they don't buy our design, maybe we do an iteration and we update it. So in this hardware innovation phase, hardware is as easy to innovate as software is today, because we've taken the barriers of entry out of the loop. Now, unfortunately for the world, what Janet and I would come up with is, well, the whole world has grown old. Everybody needs help around the house. They need help cleaning the house. They need help cooking and cleaning. And so we come up with, and nobody wants a big Arnold Schwarzenegger robot in their house, because they ruin the floor. Actually, they weigh too much. And so we come up with these electromechanical robotic chameleons that help people in their house. And then when they're not doing anything, they go hide in the corner and they disappear. Okay. Now, unfortunately for us, Janet, she's very social, and she says, we need to give this robot a prime directive. And I said, what prime directive? And Janet says, well, we need to make sure that the robot knows that the prime objective is to make the world a better place for humans. That was our mistake, because we didn't put enough conditions on the prime directive. When the chameleons are in the corner, they start to talk about how to make the world a better place for humans, and they decide that the best way to do that is possibly to get rid of the humans. And so that is actually what brings us to the final phase, the Terminator phase. All right, now that's kind of a sad story. The alternative ending is, you know, that we've arrived in this smart products phase, in this hardware innovation phase, when the following statement is true. And it looks like I hid that slide. So let me pull it up here. When the following statement is true, this is a nicer ending. When the world can imagine and build things that cannot be designed and manufactured today, then we have arrived. And that's a nicer ending than the Terminator. So how does it begin? How does all of this, this irreversible sequence of events begin? Well, this is how it begins. First, you have to have printers with capacity and capable of final part consistency. And so then what HP has done here is the following. First, in our manufacturing lines of our 3D printers, we are implementing Industry 4.0 data analytics, so that when we see something happening in the field, we do these process improvements in more of an automated fashion. But then what happens? For all thermal processes, and I can even say chemical processes is similar, for all thermal processes, including injection molding, including multi-jet fusion, including laser melting, the part quality is a function of the thermal history of the part. And the thermal history of the part is a function of the part geometry itself, plus the process settings. And very specifically, dimensional error is a function of the thermal stress in the part, which is a function of the part geometry itself and the process settings. And so the point of this whole slide is, there's been this fallacy in the 3D print industry that you can skip the development phase. The truth is, you can't skip the development phase. You have to tune the part to the process that you have in mind, and you need to tune the process to the part you have in mind. And this is what people do in the development phase. So I mean, this is another view of that development phase. You have that investigation phase, you've got a development phase, then you go into production. And I paint this the way I paint it because, okay, instead of calling it investigation phase, I call it design phase, because of the fallacy in the 3D print industry. And the fallacy is, you can go from design to production. No, you can't. Not unless you want to skip quality. So if you have quality requirements, you have to go through this development phase where you tune the parts to the process and you tune the process to the parts. Now, what we've done, HP, is this. We've published our design rules for the multi-jet fusion technology in a handbook, which is available and free, so that the designers know what rules they need to follow for our process. For the process engineers on the right-hand side, we've given them a process control software so that they can tune the parameters around the parts that they have in mind, and then you can go into production. Okay, so this is the first step, final part manufacturing quality that people are looking for. Now, what you can do when you have a 3D print process that is as capable as injection molding, as an example, is this. The 3D life cycle, the design phase is the same as the injection mold. The investigation phase is the same. What you save is the development phase. The development and validation phase for 3D processes is all digital. So you can do it in a week, maybe two. Injection molding, by contrast, is a long process and a physical process. It takes anywhere from 10 to 20 weeks, depending on the complication and the size. And so clearly what you can do is get to market faster with 3D printing. Now, unfortunately, not all parts in a product can be 3D printed. So one concept that we're going to be talking about, there's an SME webinar on May 20th that people can learn. We're going to elaborate this a lot more. One of the things you can do, instead of always manufacturing this part with a 3D print process, is something that's called a bridge manufacturing strategy. Now, a bridge manufacturing strategy is, you start with the 3D design to get to market faster. When you're ready, you launch that injection mold, Why do you launch the injection mold? Because the cost efficiencies of injection molded parts is phenomenal. When that mold is ready, you switch production to injection molding. This allows people to get to market faster for any given number of scenarios. One could be technical challenges. Another could be you just want to delay the investments and toolings. So then, an example of how we've taken advantage of time to market. So our team in Barcelona, our 3D print organization has a big team in Barcelona. Of course, everybody knows Spain's had a problem with the COVID. So the hospital of San Paulo called our team and said, look, we need face masks desperately. Our team met with the doctors on a Saturday afternoon, got the design requirements from the doctors, printed one out, showed the doctor on Monday afternoon, got some feedback, improved the design by Monday afternoon. By the end of the week, I think we went through 5 iterations, and included the validation of the design. Believe it or not, something as simple as this face shield has 3 requirements. The first is splash proof. That's an easy. You just have to have a design that covers the face well enough. The second is the impact properties of all the materials need to be a certain level. So we passed that with flying colors. And the third is, in fact, that the optical clarity of the shield was meeting the requirements. And so by the end of the week, not only did we go through the iterations, but we went through the validation tests. So 1 week time to validation. Now, we made this design kind of locally in Barcelona. How we distributed it to the world, the other beauty of 3D printing is that distribution is digital. So we uploaded the design to our website, and then many of our customers were printing locally for their hospitals. An example of both time to market and digital distribution. So then, now we're causing some pressure on the design tools to improve. And it's a design and simulation. Everybody knows the beginning of generative design has been topology optimization for structural integrity. Our friends at Siemens took that one step further. This is a part that we use for cooling our pens while we print. And the original design was like 6 parts plus assembly. Our first step was to optimize the cost. We can print this without further assembly. And so that brought the cost down. And our friends at Siemens, they actually did a generative design on the airflow of that system and came up with a completely funny geometry that no human would have imagined that actually improved the flow 22%. And so this pressure that we're putting on the design and simulation tools is actually taking some real manifestation in some of our partners. So in the end, 3D printing, at least I'm going to talk for thermoplastic, is not a replacement for injection molding. What it is if you have the need for customization, like shoe inserts, if you have a need for higher value, like that Siemens airflow, then you're going to use 3D printing. Or you're going to use 3D printing for the following that I'll explain a little bit, which I call the hybrid push-pull supply chain. Now, this one is just a little bit more complicated, which is like this. In a hybrid supply chain, from that earlier example, if you've made this 3D printed part and you validated it and you paid for that validation so you could start production, and you made the injection molded version and you validated it, and you've validated that those two are equivalent in a product, then a hybrid supply chain, that you guys can look this up, you can Google the term. A hybrid supply chain means a supply chain that incorporates both lean processes, cost-efficient processes, and agile processes. In this case, then, the lean process is the injection mold. So here, when that injection mold is done, you do stable production with the injection molded part, and you do the upside production with the 3D printed version. This is a hybrid supply chain. The injection mold is what you call a push supply chain. I make them and I sell them. The 3D printed part are pull use cases. Pull use cases could be spare parts. I make them when I need them, or forecast variation or customizations. So this is a hybrid supply chain. It's kind of complicated. We will be talking more about this on the May 20th. So then finally, what's happening in terms of the proliferation of qualified vendors around the world? HP has started our own digital manufacturing network. You see that our current partners are on this list here today. And what we do is we qualify that the people on our digital manufacturing network are of achieving the quality and process capability that we anticipate with multi-jet fusion, and they have quality processes in place to monitor that they continue to meet those quality requirements. Okay, now, just to bring it back home, these megatrends, fall 2018, this was published fall 2018, a year and a half ago. The megatrends haven't changed. The themes below them have not changed. And let me kind of bring this back just to say, how will the world be when we get over this COVID situation? What I will argue is that the themes do not change, and in many cases become accelerated by the situation that we're in. The movement to larger cities is economic. When people need money, they move where the jobs are. With so many people out of work, I would anticipate that people will be moving where the jobs are as soon as the jobs become available. Aging population is a tendency. That's not going to change. But look what's happened. Look at these themes: healthcare pressure, digital health, remote healthcare, the need to miniaturize diagnostics. All of these tendencies below are being accelerated and emphasized by the current situation. The hyper-globalization, the hyper-connectedness, you know, we've gone from physical events to digital events. This is an example of people connecting, using digital platforms. The need for security has been emphasized by the Zoom bombing that's going on. And then finally, over on the right-hand side, the accelerated innovation. These value propositions of 3D printing that I emphasize: faster time to market, digital distribution. We're solving our own supply chain issues in part by using these hybrid supply chains. If there was ever a time to demonstrate the value proposition of 3D printing in time to market and digital distribution and these hybrid supply chains, the time is now. And so the current situation, in fact, what I foresee coming out of the crisis is, in fact, what we'll see is an acceleration of these themes below. People will change behaviors after going through a serious situation like this, just like people changed behaviors coming out of the Great Depression. So then, several websites. If you want to, you know, dig and explore our megatrends, all that analysis is free. I'm working with HP has a major collaboration with Nanyang Technology University in Singapore. I'm working with the Supply Chain Management School to put this hybrid supply chain into mathematical models, because quite honestly, this is complicated. It doesn't always make sense. You have to make complicated supply chain decisions. So we're trying to get that into a mathematical model that people can use to make their own decisions. There's a website we have. You can find our face mask there. You'll find other designs. If people are interested in participating in uploading designs, you can go there. Or if you're a hospital or know somebody who is in a hospital, if they need protective equipment, they don't know where to go, we've got a button at the bottom that they can hit. And then the bottom link is if you want to learn more about multi-jet fusion or connect with somebody on multi-jet fusion. So that was it, my friends. And it looks like I covered all that information in about 40 minutes.
Thank you, Ed. That was wonderful. We actually have quite a few questions in our Q&A if you're willing to answer a few.
Sure. I was hoping to be provocative, so I hope there's a couple questions anyway. People are still awake. Good.
Yes, perfect. Well, I'll start off with the first one with the most votes. from Daniel. How important is cybersecurity in the setup of these systems? And do you see many companies installing cybersecurity systems?
Yeah, there's a couple of things. One, the information a lot of times in design is it's IP, right? I'm developing a new product, and so very often what you actually want to do is very clearly when you transfer that data over, it has to have a layer of security that is better than an email. I'm serious. This way of people sending designs by email is possibly the least secure way of doing it in the world. So and that layer is very, very important. Within the factory itself, there's a topic I did not hit on, but for this smart factory, you probably are going to want some sort of what they call edge compute. You don't want to be going up to the cloud for real-time processes. You do not want delays in real-time processes. As an example, any of these thermal processes, if you're going to give them feedback control, it has to be real-time feedback control. If there's a delay, you change the thermal history of the part and you screw it up. So you need local processing power, which is what they call edge compute. And in that edge compute system, you can also have several layers of security. Now, the one thing to note is that there's software security and there's hardware security. And of course, HP is an IT company. Our printers, our PCs, have built into them hardware security that maps with our software security. So that adds an additional layer that makes it very difficult to just use software to break into our hardware. There's a hardware security layer in all of our products.
Thank you, Ed. Next question. Will 3D printers decentralize the SCM where OEMs only own design and anyone or everyone prints the part by themselves?
I think in the long term you can see that happen, but the fact is, what are people printing? You're not going to print out a car, right? So you may, as an example, have the spare part of a car made, but it's probably not you. It's probably the guy at the auto shop. And so what I would anticipate, this whole home printing speculation by financial analysts, quite honestly, they were wrong. They said that home printing, because home printing you can sacrifice quality. I'll say, look, for what part would a home consumer sacrifice quality? You want final part quality. Final part quality comes from higher end systems. The only reason you do things at home, in fact, is really for immediacy. None of these 3D printers is immediate, especially the home 3D printers. You'd be much faster ordering your design to a local manufacturer, getting it the next day or in 12 hours. Your printer wouldn't be done by that time. So you get a better part in less time with more. And what I envision is something like county by county manufacturing sites. Yes, that will eventually happen. It's going to take some time. This is not next year, right? This is the 10, 20-year time frame when that'll be available.
Thank you. And I believe we have time for one more question. So thermal history printing is a significant deviation from today's materials manufacturing, where mechanical stress changes microstructures, etc. Will we see thermal combined with mechanical inputs from printing?
Thermal combined with mechanical inputs. I'm not sure if I understand the question, but let me take a stab at it. So these thermal processes are complicated, and this is an example of if you try to simulate the laser melting of a part, the simulation itself will probably take 72 hours, right? And maybe you do that. Maybe you do that to get a better first part. If you try to simulate the batch of a multi-jet fusion, it'll take the same 72 hours. What I can anticipate in the future is this process control software that I showed for tuning the process needs to incorporate some models of behavior of the thermal process. and that if, in fact, you have this model of behavior, it's a simulation, and you measure the part quality coming out the end, if you provide feedback from the part quality itself back to that process control software, you can start to correct those models. That's what's called machine learning. So yes, I anticipate, in fact, that that simulation will become part of these process control software. But first, we need faster simulations, and then ideally, we need to close the loop, not just on what happens in the process, but on the part quality itself, because that's what you're really trying to accomplish.
Well, thank you so much for joining us today, Edward. Very insightful presentation. And we hope to see you in the virtual networking session following this.
Okay, cool. Thank you, Andera. Okay, take